So let's talk about point continuity test. This is going to actually determine if the function is discontinuous or continuous at specific points. And then you can apply this over the whole graph at every point if you think about it. What we're going to have to do is we're going to have to see if the function is defined at that specific point. So if I plug in x equals a, do I get a real answer? And if it's no, then it's discontinuous. If it's yes, then it will most likely be continuous, but not always. So then we have to move on to step 2, which is then find the limit as x approaches a. So if by chance the limit exists and it's like 2, and we plug in x as 2 in, and those are both the same, which is step 3 if they're the same value, then it would be continuous at that specific point. If any one of these 3 steps is wrong, it will be discontinuous of some nature. So what we're going to talk about is running through using the continuity test, and you're going to have to go through all 3 steps in order to figure out what this is. So you can't just stop at one step, you have to use all 3 steps in order to do this. So on a test or quiz, homework, you're going to have to run through all 3. So the first step is determining if that function is defined at that value. So we're going to look at x equals 3. Is it defined here at that value of 3? Which, if you put 3 minus 3 in the bottom here, you can see that it divides by 0 and not okay. So if I do this, let's go ahead and do it in red. So if I say f of 3, because that's what I'm doing, I'm plugging in 3, is that defined here? So we have 3 squared minus 9 over 3 minus 3, which is in fact 0 divided by 0, which anytime we divide by 0, even if it is 0, this is going to be undefined. So we're going to say that this value is undefined. So it already fails step 1. So we already know it's discontinuous, so it fails step 1. It's not defined here, so we already know it's discontinuous. But what kind of discontinuity? And we're going to walk through a guide in just a moment, but let's go through the next step here. So the next step is figuring out if the limit exists. So we're locating or telling us, does the limit as x goes to 3 of our function, does this equal something? So we're going to have to figure that out. And one way to do that is just we use a table. We're going to use a table of values. We're going to make an x and a y table, and I'm going to do it horizontally versus vertically. You can do it vertically if you like, but let's think about 3. I'm going to think about 3, and then I'm going to think about numbers very close to it. So I'm going to go down by hundredths here, and it's better to do smaller and smaller numbers, but I think hundredths are usually pretty good. Thousandths or 10,000ths are probably even better. But if I think about it, I'm going to go up by just small values and down by small values. So this table here, we're going to figure out what the y value is approaching as we get to 3. Now, the first thing to note is if we plugged in 3, we're going to have an error. That will not be good. So now what we have to do, the limit of this function is it's going to have to approach some value. So what value will it approach? And what value would this approach as it gets smaller or closer to 3? As it gets closer to 3, what is it going to approach? That will be my limit. So we're going to think about what does this go to? Question mark. What does this go to? Question mark. These have to go towards the same exact value, or it converges is what we're going to talk about eventually. So if I substitute this value into this function, so I'm plugging it in, and I can do that with a calculator, and I should get this as 5.98. Then I plug in the next value, so I substitute this in, 2.99, in here and here, and figure what that is. I will get 5.99, rounded to the nearest hundredth. And again, we're going to get some sort of error here because we can't divide by 0. That's not okay. And if I plug in this one, I get 6.01, and this one is 6.02. Notice how this is decreasing, and it looks like it should be 6. And this one's increasing, it looks like it should be 6. So that is a way to show that my limit is going to be 6. So now we have a step 2. We have the limit existing, but step 1 fails. So what's going to happen here is this is actually going to be removable. So what the picture would entail is it's going to be going towards something, and then we're just going to take out that point, which will be at x is 3, and then it's going to continue on. And it doesn't have to be a straight line. It could be some sort of wavy thing if you want, depending upon what the function looks like. This will be a straight line, actually the line x plus 3, y equals x plus 3, and we can talk about that later. So this one, obviously step 3 will fail. Step 3 fails because this one's okay, this one's not okay. Those can't be equal if one is good and one is not good. So this one also fails. This will actually be what's called removable discontinuity. And the reason why is because step 1 fails and step 2 is successful. So whenever you have step 1 failing and step 2 having a limit, this will always be removable discontinuity. And we're going to write in where it does. It's at the point x equals 3. So we're going to talk about the 3 steps and like which one is which when those things fail. So removable discontinuity is when, this is going to occur when step 1 and step 1 fails, but step 2 it doesn't fail. So when step 1 fails but step 2 doesn't fail, that will always be removable discontinuity. Or if only step 3 fails. So there's 2 ways that you could have removable discontinuity. Step 1 and step 1 fails but step 2 doesn't. And then if they both pass but step 3 is they're reaching a different spot, then it would be different. And a picture of what they look like. So the first one, again, we have this. So that will be the one in red here. So this one goes to that one. And then the other one is something extremely similar. It's the same kind of idea, but we could have a actual point kind of below or above it. And there are certain situations where you'll see it. So that's where step 3 will fail, is if you have a limit and an actual value, but those don't match up. So the value is actually below, or it's kind of jumping below. It's kind of like jump, but not really. So we'll talk about that a little bit later and see if we have some examples. Now, jump discontinuities if step 2 fails. So if step 2 fails, but step 1 is successful, we'll put step 1 doesn't fail, then this will be a jump discontinuity. And then the last one is all steps will fail. It will not have a limit, it will not have this, therefore if they're both not good, then you can't have the last one equal to each other. So let's walk through 2 more examples, and then I would like you to try one as our last thing today. So we're going to have g of x, and it's equal to a piecewise defined function. So we're going to figure out if this is jump, infinite, or it is removable, or neither of them actually. So step 1, let's plug in a value. So if I put g of 1, so we're looking at specifically 1 here, g of 1 is in this case equal to 2. It tells us it is equal to 2. So when I plug in 1, well, g of x is 2. Done. So we know that if we have the value 1 here, this is equal to 2. And then let's keep putting in, we're going to do values that are really close to 1. And again, I think hundredths are okay, but in theory, you should do smaller and smaller values. So just because of speed's sake and writing down sake, we're going to do hundredths. We should do at least 10,000ths probably, or even smaller and smaller, which our graphing calculator can do that. And I'll walk through that eventually. So now let's go ahead and try this next one. So let's find the limit. So step 2 is seeing if the limit exists. So does the limit of, or as x approaches 1 of g of x actually equal something? So we're going to figure that out. So plugging in this value is less than 1, so we plug it into this function. So we do 0.98 squared, which is 0.98 times 0.98, or 0.9604. Now 0.99 times 0.99 is 0.9801. Now, what we're going to do is we're going to plug in this value. Notice that's bigger than 1, so we plug it in here. So 3 times 1.01 minus 1, which will give me 2.03. And this one will be 2.0. 6, I believe. So if we look at this, this is approaching 1. This should be approaching 1, and this approaches, it looks like it goes to 2. Notice how 1 does not equal 2. Therefore, this doesn't exist. So if this doesn't exist, or it fails, but this one passes, remember that will be that jump discontinuity. So this one is jump discontinuity at x equals 1, because the first one is passing or doesn't fail, and then the second one doesn't exist because it approaches 1 from this side and 2 from this side for the y values. Our last example here is m of x here, so let's try it again. Let's make a chart here for speed's sake. 1, 2, good enough. So now step 1, again, we're going to substitute in the value of 1. So we're going to do f of 1, which is equal to 1 plus 2, all over 1 minus 1, which is definitely 3 over 0, which is failing or undefined. So this would fail that first step. So it is discontinuity, or has discontinuity, sorry. It's a discontinuous function. But what kind? So step 1 failed. Now let's check the next one. So again, we're going to plug in 1 because we're doing x's are 1 and 1.01, 1.02. Let's do 0.99 and 0.98. Plug those values into the function. So using my calculator, plug this value in here. So 0.99 plus 2 over 0.99 minus 1, what is that value? And if we do that, we should get that this is negative 299. This is negative 149. If we plug in this one, it's it's an error, and this is a 301, and this is like 251-ish or so. So as we can see, this is going really small. This is going really big. If I even put in smaller numbers, it would get really big, and this would get really, really small. So this one doesn't exist. No, the limit doesn't exist here. And if we look at the graph, we'll notice that this keeps going up and up and up and up and up. You'll have something that goes like this, and then the other one will go like this, because it will go up towards infinity and down towards infinity, hence where those numbers are very different from each other. Therefore, step 2 and step 1 fail this, therefore it is infinite discontinuity at x equals 1 here, based off of the rules we talked about before. So please try this last one on your own, and we can talk about this later if you need more help. So if you tried it, you should have got steps 1 and 2 fail. You should show the work for that, and then it'll be infinite discontinuity because they both fail at x equals 2.